Introduction to proofs. Proof what? Proof theorems. What is a theorem? It is of some importance according to some level or according to the topic. Proposition is a theorem, but it is a little less important than the statements of theorems. Lemma. Lemma is less important than theorems and propositions, but the proof of lemma usually depends on axioms, elementary properties, and some remarks. And the lemma is then used to prove theorems or propositions. Corollary. These are results that come out as applications of theorems. Usually in books you will see items with these names: theorem, proposition, lemma, corollary, and students usually wonder what are the difference between them. So it is here, theorem is the more important things, the proposition less important than theorem. Lemmas are results that are used in the proofs of theorems, and the proofs of lemma depends on elementary axioms and properties, and corollaries are applications of theorems. So, okay, this is to know what these terminologies are. In here we will learn a few methods of proofs. First method is called direct proof. A direct proof, we use it to prove a conditional statement, which says if we have P, a statement, then we get Q as a result. So we assume P is true, we are having it, and we will use all possible things: axioms, definition, previous theorems, and rules of inference. We have already learned. We use all these mechanisms to show that Q is true. So this is direct proof. You have information, you use it, you play with it till you get to the results. And to see an example, we need to recall what is the definition of an integer to be even. It is even if it is of this form, 2 times k, where k is some integer. And it is odd if it takes this form and equals 2 times k plus 1, where k is some integers. It could be minus 1, 2k minus 1. Okay. So to see an example of what we mean by direct proof, let us prove the following statement or the following theorem, which says that if n is odd integer, then n square is odd. So we want to prove that simple statement, and we will use direct proof. Okay. So we begin with a direct proof of this theorem. We assume that n is odd. So here I want you to get used to this statement. This is called the hypothesis. The hypothesis al-mu'tayat, the hypothesis of the theorem. So this statement having n to be odd, this statement here is called the hypothesis of the conditional statement. So assuming n is odd, that means n has this form 2k plus 1, where k is some integer. Now square it, and then we go all the way. We get the square to be 2 times some integer plus 1. And we conclude that n square is odd integer. So it is an easy proof, but this shows us a direct proof. We used the hypothesis, we played with it, and we reached the conclusion. So this is direct proof. Another example of direct proof is the following. This example says, give a direct proof for the following. If m and n are both perfect square, then n times m is also a perfect square. What a perfect square means, an integer is a perfect square if it is a square of some other integers, like 4. It is 2 square, so 4 is a perfect square. 9 is a perfect square because it equals 3 squared. 25 is a perfect square because it is 5 squared. But 24 is not a perfect square. Okay, let's see. Now let's follow the proof to direct proof to prove this theorem. So to produce a direct proof, we assume m and n are perfect squares. So again, this is the hypothesis. So we have the hypothesis of the theorem. The hypothesis. So this here is the hypothesis. Okay? And this here is the conclusion. I want to emphasize that. Hypothesis gives the conclusion. And we want to work a direct proof for that. Okay, so we start with the hypothesis, having m and n, each of them being perfect square. That means m is a square of s for some s, and n is a square of t for some t. That's what we are assuming. M is a perfect square, so it is something square, and n is the same. Now multiply m and n, we get that. Now notice we can write m times n all the way to be st all square. So m multiplied by n is a square for some integer, which is st. So m times n is a perfect square, and then we reached the proof. So these are simple proofs, simple results to prove, but they demonstrate what we call direct proof. You use the hypothesis, play with it, and you reach the conclusion. This is direct proof. Okay. Now we will see another kind of proofs, which is called proof by contraposition. And this is not a direct proof. This is not a direct proof. We will not be using the hypothesis and going to a conclusion. We will do it some other way. So proof by contraposition. Remember contraposition? It means contrapositive. Here we go. Do you see this statement here? B, if P then Q is equivalent to not Q gives not P. We call this contrapositive. And this contrapositive is very important in mathematics and in computer science. This way is very helpful for doing proof. Now, let us see proof by contrapositive, how it works by doing that example. Prove that if n is an integer and 3n plus 2 is odd, then, so we have this conclusion, n is odd. So we have this assumption, n, 3n plus 2 is odd. We can say this is P. N is odd. This is Q, the conclusion. And we will go by contrapositive. We will prove the following. Let me write it in red. We will prove not Q will give not P. Don't let this arrow confuse you. We can write it again. We want to prove, let me write it again here. We can write not Q gives not P. So it is the same read in here and in here. Okay, so we will assume, we first assume that, okay, good. So what we do here, I want to show you that if we think to work a direct proof, then we will reach a dead end. It will not be helpful. So direct proofs, the ones we learned already, is not the appropriate way to use. And this is an example to show that. So if we try to work a direct proof, we will say we will start from the hypothesis, which says 3n plus 2 is odd. So this is the hypothesis here, and this is the conclusion. Now, if 3n plus 2 is odd, let's play with it That means the 3n plus 2 equals 2k plus 1 for some k because it is odd. Then what we do next? Like if we want to say, okay, we want to prove n is odd. So maybe we will say, okay, that means n equals 2k plus 1 minus 1, 2k plus 1, sorry, minus 2 over 3. That equals 2k minus 1 over 3. And then this gives n squared equals 2k minus 1 all squared over 3 squared. And then is that gonna help me to reach the conclusion? Is that gonna help me to show that n is odd? It does not seem to help. So direct proof. So first we attempted the direct proof, but it was not helping. So we will work it using indirect proof by proving the contrapositive here. So we will go to here I'm saying a proof by contraposition. We will say that not q here is n is odd. So not q means n is even, because an integer, it must be either odd or even. If it is not odd, then it is even. So the negation of q is to have n to be even. That means n equals 2k for some integer k. Now, okay, remember what we want to prove. We want to prove that not q. Right? So we assume here, I mean, we want to reach having n not even and want to reach that 3n plus 2, n is even, and we want to reach that 3n plus 2 is even. So we negated the conclusion and negated the hypothesis, but we are going from the negation of the conclusion to the negation of the hypothesis. And if we can prove that, then we prove the original statement. So not q is n is even, which means n equals 2k for some k. Now compute 3n plus 2 and compute it all the way. It will come out to be 2 times some integer, 3k plus 1. So this is even indeed. So we ended with 3n plus 2 is even. So good. So we proved not q gives not p. So we proved it, but we know this is same as this is statement, and then this is it. We reach the proof. This is the contrapositions. I like to call it contrapositive. Okay, so it is a very powerful method for proofs. Okay, another example for contrapositive. It says we need to prove that if n equals a times b, n is some integer, a and b are integers, then either a is less than square root of n or b is less than square root of n. So we will prove it by contrapositive. So this is statement from here to here, we call it q, and this is statement we call p. So what we want to prove that not q gives not p. But what is not q? So to negate that, this says a less than square root or b less than square root. The negation will be not this and not that. So let me write. So what did I write here? Sorry, I need to fix that. Here it should be not b, not p. Okay. Okay. So let me make what I'm saying clear. Not q is the negation of not q is the negation of n as a less than or equal square root of n, or b is less than or equal square root of n. So the negation will come out to be negate this, not a less than or equal square root of n, and so we are using De Morgan's law here, not b less than or equal square root of n, and then the negation of this part here, the negation of this part will be the opposite. A is greater than square root of n, and same thing here, b is greater than square root of n. So if we want to start with not q, this is now not q. A is greater than square root of n, and b is greater than square root of n. Now, once we have that, then a times b is greater than square root of n times square root of n, which is n, and then we got ab is greater than n, which means ab does not equal n. And what is that? ab does not equal n. This is the negation of p. So good. We started from the negation of q and ended. So if I write it here, the negation of q, we started with the negation of q and ended with the negation of p, and we are done. Okay. Another kind of proof is proof by contradiction, and it is a very powerful way of proof, and it is need to be not easy to construct actually. And the best way to introduce it is just to work an example on it. The idea behind such a proof is the following. Assume we want to prove a statement. Assume want a statement P to be true. So, how the contrapositive will work? We will suppose that statement is not true. So we will suppose the negation of our result, the result we want to prove. Assume P is false. And then using that, using this information, I will get some conclusion. Okay, and then I will play with that conclusion, and maybe this falseness here will help me to get, so I will call this conclusion 1. So I play with conclusion 1, and maybe assuming P is false will help me also, along with conclusion 1, to obtain another conclusion, which I call conclusion 2, but surprisingly, these two conclusions are contradiction for each other. None of them will happen. Like, I mean, if we call this conclusion to be Q, some statement Q, this conclusion will be not Q. So I will have conclusion 1 Q, conclusion 2 says not Q. Oh, how could that be happen? To have a thing and its contradiction at the same time. So something wrong has led me to this. What was wrong? My original assumption. My original assumption was wrong. Assuming P is false was the wrong thing to do. Oh, okay, so P must be true. So this is proof by contradiction. And we will demonstrate it using this example here. Now, proof 2, square root of 2 is irrational. Irrational. Rational number mean we can present it as a fraction. Rational numbers, any rational numbers is a over b, where a and b are integers, and b does not equal 0. So if any number r is a rational, if we can write it this way. Now, this says proof square root of 2 is irrational, so it cannot be written that way. So it asks us to prove this by contradiction. And see what we do. Now, we will follow it by contradiction and say assume P is false, which means not P is true. So here we are assuming P is false. Okay, and this will lead us to contradiction. This says assume square root of 2 is rational. The theorem asks us to prove that square root of 2 is irrational, but we went the other way. We said, okay, no, assume it is rational, and let's see what happens. We will lead to a contradiction. Okay, now if we assume not P is happening, which means P is false, let me emphasize it, P is false. Now, what we get? That means we can write 2 as A over B with A and B integers. B is not 0. And we can assume that A and B have no common factors, right? We can assume that. Like, if it happens A and B is like 24 over 18, we can say, oh, okay, divide by 3, we get 8 over 6. Oh, okay, divide more by 2, we get 4 over 3. So this is what we mean in lowest term. So as we assumed square root of 2 is the rational number, then certainly we can write it as A over B, such that A over B has lowest form. There is no common factor between A and B. Fine. This is conclusion 1. Okay. So this is what I said just right now. This is conclusion 1. We will proceed and will conclude conclusion 2, which is a contradiction to conclusion 1. And let us see. Now, if we have square root 2 to equal that, then square both sides, we get this, okay? So, A square equal 2 times B square. That means A square is even. A square is even, that means A must be even. Good? Because if you take an odd integer and square it, the result will be odd. That means if the square is an even, square of some integer is even, then that integer was already even. Good. So which means 2 divides A. Okay? Good. Now let's go back to here and substitute for A the 2C. Then we get 2b square equal 4a square. Divide by 2, we get that. Oh, so b square is even. Aha, so b is even. What? Now b is even, a is even. These two things will make us conclude that a and b have common factor. Have common factor. Okay? So they have common factor. And this is conclusion 2. So conclusion 1 says A and B have no common factor. Conclusion 2 says A and B have common factor. And we got here contradiction. Contradiction, so I can see here. Okay. So we reached a contradiction. This is what we mean by proof by contradiction. Again, actually, it is usually difficult for students to understand what we mean proof by contradiction, but this diagram here gives you an idea. So let me go and circle it with red. Again, if you want to prove that some element, some statement is true, we go and assume it is false. We use that to get some conclusion 1. Use that conclusion along the false statement to get conclusion 2, which contradicts the first conclusion, and then something wrong happened. What caused that contradiction to happen? The original assumption of the falseness of the statement. So we were not supposed to assume that falseness. So that statement must be correct. Okay. Let us continue. Okay. Proofs of equivalence. Okay. Now this is very, very commonly used in mathematics. It says some statement P is equivalent to Q, which means P gives Q and Q gives P. And then we will say if and only if. An example here, see. n is odd. N is odd. So this is p. It's here says n square is odd. This is q, and here we are saying if and only if. That means if n is odd, then n square is odd. And going the other way, if n square is odd, then n is odd. So we will say n is odd, if and only if n square is odd. So how to prove such equivalence? We will prove the two directions. We just work the direct proofs or indirect proofs, the contradiction, the contrapositive, to prove this part and this part. So proof of such a statement, if and only if, usually contains two parts. We prove this direction, and after we finish, we say conversely and go prove the other direction. We may use contrapositive with any one of them. And to make this clear, we need to do the following example. And this is very commonly used in mathematics. Let us see. It says, show that these statements are equivalent. This is very commonly used. Are equivalent. Are equivalent. What that means? We will show that B1 gives B2, B2 gives B3, and B3 gives B1. What we then have done, like here, B1 gives B2. So we will assume that we have B1 in hand, play with it, and prove P2. Then again, we will assume P2 is in hand, play with it, prove P3. And then we assume P3 is in hand and go prove P1. So in this way, you can go from any one of them to the other. Okay? So like if and we are saying here P1 is equivalent to B2 is equivalent to B3. So that means P1 is equivalent to B3. So does P1 gives P3? We say yes. We prove P1 gives B2, B2 gives B3, and that means P1 gives B3. Okay. And P3 gives B1 the opposite way. Okay. So let's do the proofs for these statements. So here at the beginning we will show that P1 gives B2. P1 says n is even. So n has this form. Consequently, n minus 1 has this form. So it is 2 times k minus 1 plus 1. So n minus 1 is odd. Okay, so we have reached B2, which says n minus 1 is odd. So this was direct proof. Okay, now to prove B2 gives B3, we start with P2, which says n is odd. And then we want to reach that n square is even. So n is odd, n minus 1 is odd, sorry. So n minus 1 has this form, 2k plus 1 for some k. So n equals that. Now square n all the way here. We get 2 times some integer, so n square is even. So P2 proved P3. Now we want to prove P3 gives B2, which means if n is even, then if n square is even, then n is even. And we have already proved that in example 1, very first example. And then we are done. So this is the way to prove equivalences. Now, at the end, one way to prove theorems is counterexample. We talked about counterexamples before. Now, to show that this statement says for every x, p of x happen. And now we want to show this is false. It's not true. It's not true that for every x, p of x happen. Why it is not true? Because there is an element for which p of x does not happen. So this is called counterexample. So we need only to find a counterexample for which p of x is not happening. And this is simply can be given here. Show that the statement every positive integer is a sum of squares of two integers. Every positive integer, say x, it must be a square plus b square for some a and b. Is that true? Maybe yes, maybe no. Let's try numbers. Let's say 3. Can I write 3 as squares of two integers, like 1 square plus 1 square? No. 1 square plus 2 square? No. Okay, so I cannot. So p of 3 is false. So let me write it here. So, oops, too many so's. So, okay. So, this is not true. For every x, p of x is false, because we just found a counter example. So these are all the methods of proof, and to this point we are done, and thank you.